is about fluid engineering for low carbon designs. Um, I think best to start the journey thinking of yourself in a tunnel. Imagine you're a fluid traveling down a tunnel. Imagine it's a car. The car is the fluid going down the tunnel. Um, and you as a fluid could be steam, which is at very high temperature, or you could be at very low temperature, which is very common in low carbon designs. So think of that analogy traveling down this tunnel when you want to discharge your heat. Um, Pretty easy if you're steam, but a little bit more difficult if you're at low temperature, which is very common for low carbon designs. And then if you're going down a tunnel and the tunnel's got twists and turns and goodness knows what as you're driving, that's resistance. And as an engineer, you've got to consider how that fluid is going to get round the various junctions. Um, so in this first slide, I thought it appropriate just to show you two equations because um, I've been in the industry 45 years now for my sins, and there's not many equations in building services you've really got to pay much attention to, but these two in fluid dynamics are quite important. One is the DRC equation on the left-hand side, which you haven't got to work out because CIBSE Guide C um, gives you gives it gives you the answers in pipe tables. The equation on the right hand side is important because heat is equal to the mass of fluid flowing times the specific heat capacity times the delta T, the temperature difference. So clearly, if you increase the delta T, you reduce the mass flow. And that's what low carbon design is all about, is trying to convey heat um, with a very fairly high temperature difference. So I just thought I'd give you that analogy to going down a tunnel because it's quite important as we come onto the subject. Okay, so on the subject of heat, um, this slide illustrates to you very much what was common for the last probably 40, 50 decades. Low temperature hot water often was delivered at 82, 71, which is a temperature differential of 11. That relates to imperial Fahrenheit temperatures used in industry. But we've now changed because we want to obviously incorporate condensing boilers and heat pumps and other renewable energy sources. Um, and they require lower supply and return temperatures. So the graph on the right hand side top just shows you quite typically how the efficiency of boilers, for example, change from condensing all the way up to down to traditional boilers. So efficiencies in the past for a traditional boiler probably would have been in the 60s, 70s, possibly 80%. But now with condensing boilers and low return temperatures to condensing boilers, we're up in the upper 90s quite easily. So for heat pumps, which are very common nowadays as a renewable energy source, that bottom graph shows you what is quite common with heat pumps is that they're trying to extract energy, obviously, from the outside air. And as that outside air reduces to the right-hand side of that graph, as you can see, the efficiency of the heat pump drops away. So typically, as the winter hits the UK say around 12 degrees or 10 degrees outside, the heat pump efficiency drops because it has to do more work to extract heat from the outside air. So this slide was all about heat and how, what's the efficiency of transferring it. So if we say that a modern flow temperature is particular on the radiator scheme, you might say you'll send it out for the condensing boiler, maybe 50 degrees, and you might hopefully send it back at say 30 or whatever. The temperature difference obviously has an important effect on the heat emitters. And therefore, particularly with air source heat pumps, for example, you're going to need larger radiators to dissipate that heat in the space. So that photo shows you not a typical radiator, which could be 2 times bigger than a traditional radiator operating at 8271 to get the heat out into the space from a heat pump. Or a condensing boiler, for example. So that equation, Q equals m dot Cp delta T. If the temperature difference is 20, then the flow rate is lower. That's good. But to get that heat into the space, you're going to need larger radiators. And I won't go into the technical bit of that, but it's all related to log mean temperature difference between the surface temperature of the radiator and the temperature of the room. So we move on to flow of fluids, which is quite an important aspect when we're considering low carbon designs. Um, this particular slide is showing you what has been traditionally used in industry, where we use a constant pump that provides a constant flow of water. And the diagram on the right shows you a typical application in a commercial application where you use a 3-port valve. So on the balanced flow, you've got a pump which is constant running, and the air handling unit on the right-hand side is controlled by that 3-port valve. So where the air handling unit doesn't want heat, that 3-port valve diverts the water down that bypass line and back to the boiler. This method of control has been very common for many, many decades. But as you can imagine, with a constant pump running, there aren't any savings in flow rates. So constant fluid delivery is a very traditional thing. Next slide is variable fluid delivery. So this is far more common nowadays in commercial buildings. So variable flow systems is all about the pump responding to what the demand in the building is. So the pump senses pressure in the system. So you can imagine if a control device or a fan coil, for example, closes its 2-port valve, it will affect the pressure in the system, and the pump senses that and reduces its flow rate. There are many, many devices in the industry to deal with variable flow of water in systems. That diagram on the right-hand side is only one of many options. But what you have in this particular example, it happens to be a chill water beam, but it could be a heating emitter. You've got a PICV, that's pressure independent control valve. You may think it's just a normal 2-port valve that closes on and off, but essentially it's got a spring in there. And it allows you to turn that 2-port valve off or control it, irrespective of the pressure in the system. It has a spring basically that takes energy out and allows the two-port valve to close. So two-port valves in these systems are very common, but why do we reduce the fluid rather than have it constant? And the simple reason is we save energy. So if you reduce the flow rate by half, the pump energy reduces by 12.5%. So you might think to yourself, well, that's good news. We can send water out at a lower temperature and we can increase the differential to say 20 or even 30 degrees and we get low flow rates and we can control it. But the story is not as clear as that. Um, and the next slides will show you why. So the summary on there is low flow and low temperature designs are not without issues. Okay, so the first thing to decide, and it often has not been a decision in the past, many decades before now, choice of materials, because people had steel, people had copper, they had galvanized steel, and possibly some stainless steel. But nowadays the choice is enormous. So I've started with plastic, and you might think, well, all plastics might be the same, but they're not. Particularly when you put heat through the material. So the graph on the right-hand side is showing you um, how these materials um, perform under various temperatures. So you can see that PEX, which is polypex cross links, um, is performing the best. And the worst performing is the PVC, polyvinyl chloride. So as an engineer, if you're going to plastic materials, and plastic's very common nowadays, you see it very widely, you see it in DIY shops as well as commercial installations. You have to consider what temperature of fluid you're putting through that. Low carbon design is, you know, you're putting fluids at low temperature, but you need to be careful because there might be some situations where the system um, goes wrong and you're putting fluids through that pipework at much higher temperature. So thermoplastics lose strength to pressure and tension with increase in temperature. Um, the thing to consider with plastic pipes is the friction loss because you're passing the fluid down a pipe and you've got to turn corners or branch off. And I thought I'd give you an illustration of a crimp fitting, um, which is particularly common in the industry now. And those pictures show you the fittings and how the pipe goes into the fitting and they crimp it. But just be aware as engineers when you calculate friction losses that these fittings have their own tables for K values. Um, so very typically they could be 15% higher overall on pressure losses through the system. So I think that's a really important thing to consider if you do go plastic, and there's nothing wrong with that. Just be careful of the fittings and how you approach that in design. Okay, so coming on to the more common material of metal, as I said, steel, galvanized copper, and stainless steel are common pipework materials. But increasingly, because metals are expensive and economics, thin wall pipework is becoming increasingly common. And these thin wall pipeworks, which are available in majority of materials, are crimped. So as I said previously, you've really got to check out the pressure loss of these systems, but also bear in mind that you've got a thin wall pipe. It's lighter, but if you don't look after that system, and I'll come on to this later, if you don't look after it, you can end up with problems a lot quicker than a traditional pipe that is thicker, for example. So plastic, you don't really need to worry about mixed materials necessarily, but when you come to metal, you do. Um, lead, and there's plenty of lead pipes still in the world underground. Steel and galvanized pipes were the most common materials until copper and stainless entered the market. All these materials are now available as mixed wall versions. So you need to avoid mixed metals where possible, and water quality is even more important. So if you're going to have mixed metals, and you may see this in existing systems where there's galvanized pipe and copper pipe, you just got to be careful with the galvanic series. You've got to stay close to each other. And if you do choose things that are a bit further apart in the galvanic series, you need to exclude oxygen from the system, which you normally would do in a heating system. But you probably need to break the electrical path at joints using different mixed metals. That's just a heads up on mixed metals. Not always a problem, but well worth knowing. So we've covered heat, we've covered flow, we've covered friction, we've covered thin pipes. Now we're coming on to the more sort of issues of low carbon design, which you may not be necessarily acquainted with. Um, so low carbon heat sources are naturally encouraging low circulating water temperatures and low flow rates, which can impact the ability to commission a system, obviously direct the water where it wants to go, and maintain good water quality. So I've just shown you only two images there, because I've got thousands of them. The image on the left-hand side is just a pipe that's probably been in there 20, 30 years, and it's not necessarily a low carbon design, but I just wanted to show you that, the inside of pipes, you can get scale deposits and biofilm deposits. And when you get to this level of build-up of deposits in a pipe, you get some serious issues going on in the system. Um, and the issues can be as simple as sensors, like this particular picture on the right shows you sensors from a boiler. That's a new sensor where my pointer is, and that's an old sensor. And the corrosion affects the control of that thermostat or whatever it is in the boiler. So it has an impact. You have to look after the water quality. Okay, so water travels down a pipe, and if you're going low carbon design, um, the flow rates can be pretty low, and the water can become pretty sluggish. What I mean by sluggish, the water velocity can be low. This impacts a number of things. So reduced flow rates, and this is all associated with low carbon design, can create slow moving pockets of water where it may be difficult to get water treatment into these areas, and therefore biofilms and sulfate reducing bacteria can cause corrosion issues. This diagram on the right it comes from a research paper actually, but it's still relevant today. In that the inside wall of the pipe, that's the grey is the pipework wall. You get biofilms building up, and the diagram to the right is the same pipe, but it's under higher flow conditions. And this is all to do with boundary layers, which is a fascinating subject, which I won't go into. But at the boundary of the pipe, um, if if the flow of water is not sufficient, you can get these biofilms building up. If you have higher water velocities, you're creating some turbulent action on this boundary layer, and you're less likely to promote the growth of biofilms than you are in a low flow condition. This is all related to closed systems where the water quality has not been managed particularly well, and biofilms get a chance to establish themselves. And this sulfate reducing bacteria, which is very common in heating systems, doesn't need oxygen at all. It's in the absence of oxygen, it lives. It lives under the biofilm, and it happily produces hydrogen sulfide, which pits the pipework, and you get corrosion. So sluggish water, poor water quality can lead to biofilms and could lead to corrosion. So you might think to yourself, well, I'm never going to have these problems because, I've put all these valves in around the system and I'm making sure that the water's going where it wants to go. But it comes back to the issue of not just the design, but the commissioning, because you could design a system with flow rates which people can't commission. In other words, they're too low. CPC Guide recommends that, or it says that ultra flow rates occur below 0.015 liters per second. Now that is not a lot of water. That's very low flow rate. But should we be designing below those low flow rates? Well, people do, and it's extremely difficult to set those flow rates up in commissioning. There are devices on the market that will do that. But my approach would be that second paragraph in situations where individual terminals have low design flow rates. A single flow measurement and regulating device could serve a group of terminal units. So instead of having all these terminal units putting heat out at very low flow rates with their own control valves, maybe just put one commissioning valve in. And that table on the right hand side, just above a commissioning valve, just shows you, there's very little differences. You've got all these settings on the left hand side, and if you went to setting 1.8, which is 0.0146, about 0.015, whether you have the setting on one or whether you have a setting on two, the variations, the percentage variations are very low. You're down to levels which you just can't commission. So my advice is do not go to very low. Look at your flow conditions, what you're trying to achieve in design, and try not to go below 0.015 because you can't set it up. Okay, so you're down to low flow rates, you're down to low temperatures, and you may be down to sluggish water. Bacteria and biofilms may be an area you might want to sort of stay clear of and say, well, that's down to the water treatment company that looks at the system. But it's really important to consider it in design. As I've said there, these bacteria multiply between 20 and 45 degrees. Now, In the past decades, this wasn't an issue because we were running at 82, 71, or we were running steam at 120, 130 degrees. But as flow rates reduce, and the water becomes sluggish, bacteria can settle and adhere to the pipe walls, which is what this biofilm is. Um, and this is particularly relevant where Pseudomonas is present in the system, and it will be at very low levels. It comes in via the mains water, but it can rapidly multiply, and it's one of the bacteria that's largely present in biofilms. But you may think, so what, why is this important? Well, it's important because Pseudomonas is like a jelly, and at worst, it will block the pumps and make them fail. Um, at best, it will block your pipes and radiators and other things. So we need to be really on top of water treatment, even when it's a closed system. So hence my heading on the next slide was we've lost the sterilizing effect. Um, I, as a steam engineer many years ago, never worried about bacteria because 120, 140 degrees, it cannot exist. But low carbon designs, you've got to be careful. So um, they cause corrosion, biofilms, they reduce flow, and particularly they reduce heat transfer. Um, I've illustrated a diagram in the bottom left, which is copper pipework, for example. Yep, copper pipework has to oxidize. You get a green sulfur oxide on the inside. But what you don't want is biofilm on the inside, which comes on top of that oxidization. Because you can get corrosion, and even in copper pipes, they will fail. They get pitting. So these diagrams to the right just really just sort of child's play, really. They're showing how a biofilm grows, builds up. And the bacteria comes from, where my pointer is, it comes from floating bacteria. It comes in via the mains water. And if your water quality is not good, it will create these biofilms that seed the water. So you'll end up having to cleanse the system, putting chemicals in to get rid of this biofilm to control the water quality. And once you get into that situation, it's extremely difficult to get those systems back to normal operation. Um, Once you get rid of the biofilm, so well, how did it get there? Was it because the water velocities were too low? Did I have control valves closing many items of the system off so the chemicals couldn't get through? Very simple questions to answer. So, in this pipework journey, um, I've touched upon heat, I've touched upon resistance, I've touched upon frictional fittings and how you need to consider those. Um, and the one that people do forget is improving water quality. Um, it's fine to design a system, it's fine to get to PC, get an O&M, and then think the job's done. But ongoing water quality and who's responsible for that is really important. So hence it becomes crucial that systems remain dosed with an appropriate corrosion inhibitor, but they need to receive regular microbial monitoring and may require biocide control. So low carbon designs require greater frequency than traditional systems due to the lower temperatures, which promote growth, lower water velocities, which can inhibit good chemical mixing. So it's certainly more cost effective to maintain microbiological control rather than to try and clean up a system supporting an established corrosion issue or microbial issue. Corrosion is very, very, very expensive. Okay, so I hope I haven't dragged on too long in various subjects. I've tried to keep it a little bit um, overall. So in summary, don't forget the heat and flow equations. Look in CIBSE Guide C when you're selecting pipework, um, and just be aware of the water velocity you're going down to and the flow rate. Choice of materials, nothing wrong with plastics, but be aware that they have limitations on temperature and they have different frictional resistances. Water flow rate and control, really important. You know, if you're down to low, ultra low flow rates, consider whether you could serve 3 or 4 terminals for one control valve, for example. Try to keep the simplicity a bit more. Think about, are the chemicals going to get around these systems? So water velocity, water quality, and then finally the management of that in an O&M manual. Thank you. I think we're over to questions.
Thanks. We have one question in the chat.
Oh,
I could start with that, perhaps. Chi Chung, Equans UK. Can you coat the pipework with nano coat to mitigate biofilm buildup?
no. The we're in the practical world of we're in the practical world that materials come from all parts of the world. You inhibitors can contain certain inhibitors contain solutions that will line the pipework and help, but I'm not familiar with the particular chemicals.
Sorry, I would just like to ask a question. Basically, is if I can't coat the pipework itself, is it possible to coat the outlet with like a graphene nano coating? So, because that would help to alleviate the pressure of basically biofilm buildup. So, because nothing, it won't actually bond, it won't actually stick to it or attach to it. So, I was just asking, I'm just wondering if that's possible. Is that a choice that could be done as an option for maintenance?
Do you mean in an existing system?
Yeah, so on an existing system, for instance, we get heavy scale build up and biofilm build up on an outlet.
Yeah.
To manage the outlet itself, if just say for instance we put a new outlet on, replacing the tap, etc., but we nano coat that with like a graphene coating. So because graphene doesn't bond with biofilm, etc. So it's a very smooth surface. I think it is. I was reading up on this sort of scientific research on it basically as an option. I know nano coating now is the cost of it's gone down so much because it's been used in a lot of electrical industry products, etc. So the cost of that's gone down a huge amount, and they last about 7 years. So I was wondering if, with technology like that, can it be applied to water systems to help reduce the risk, basically?
Okay, so I think you're referring to open systems like hot and cold water coming out of taps.
Yes, that's correct. Yeah.
Yeah, the answer to that's no, because of the water hygiene regulations and the quality of water that has to be delivered. You can't add any chemicals to those systems or coat them in any way.
Thank you.
Yeah.
Sorry, Mark.
There's another one in the chat, I believe, from Jankowski. Did you come across that there was significant flow rate difference reading between PICV and orifice? I had project where it was 20 to 40%. All the straight sections before after valves were maintained. I'm not quite sure I understand that myself.
Yeah, what I mean, PICV has a setting that you will set it and you should achieve a specific flow rate.
Yeah,
And you put the orifice to double check or validate PICVs, or some PICVs didn't have the function to measure it.
yeah.
And I had one project where there was significant difference between the two readings, which nobody could explain.
The problem with PICVs is that the spring can get clogged up. So you can see variations where because it's quite a complex bit of kit inside in that unit. If it gets fouled up, it could easily not replicate what you're measuring across that orifice plate.
Yeah, that makes sense. And there is quite some test regime for PICVs as well. I came across at BISRIA. There's a test methodology for PICVs.
Yeah, there's Viscera, I had to work there many years ago. Have got some very good publications on water commissioning. Um, One of the experts in the field is Chris Parslow. Um, so if you Google Chris Parslow, it'll come up with a lot of his publications that he did at BISRA as well. Um, it's an interesting field. I just got to you just got to be careful of ultra low flows because obviously low flows are associated with low water velocity, but um, there just becomes a point where people can't commission it. But there's a very good point there about PICVs and are they actually controlling the water to what you desired?
Well, anybody for any more? We haven't got any more in the chat, but you're welcome to just come off mute and put your hand up and have a question. Sam.
Hi, Richard. Hi, Nigel.
Hi.
Quick question on, apologies, I missed the start, but I think what you were talking about is designing around low flow rates causing issues with, I guess, biofilm and the like.
Mm.
Is it really the low flow rate or is it the low pipework velocity that is the driver for the issues?
Well, the interesting thing is that um, we don't. I How can I put it? Most people don't go below 15 mil pipe,
Mm-hmm.
half-inch pipe, and these ultra flows. Yeah, you might say, well, they suit themselves to smaller pipe sizes, but practically, the industry hasn't gone down that route. It's a combination of temperature, low temperature, and low water velocity, which we've lost that sterilizing effect. That's the problem. So we've just got to pay more attention to water quality. And it's not all systems, but systems which started off life with a good inhibitor, some good cleaning regimes, because BISRA, the commissioning is all to do with cleaning out the system and setting it up correctly. And BISRA guides are pretty good on those, as are SIBSI as well. There's a number of things. I wouldn't put my finger on one that causes these issues, but yeah, it's becoming more frequent.
Yeah, that makes sense. Thanks.
I've got one for you, Nigel. When you've got a
Yeah.
mixed metal system,
Yeah.
I think it can be that the water treatment can become a source for the bacteria, a food for the bacteria even. So there are very complex water treatment regimes that are advocated for mixed metal systems. Is that something to
Yeah.
avoid, or are they
Well,
okay?
yeah, the water is an electrolyte basically, as you'd imagine. But I've come across it more in existing systems, particularly copper and galvanized, where the galvanized breaks down and the zinc then goes off and deposits on the copper. Um, Copper and steel, not an issue. Um, it's not that common, actually, if I was to be honest. So, yeah, water treatment, in modern systems, it's not that common. So water treatment can deal with it.
Thanks. Anybody else? Oh, sorry, I put my hand up for some reason.
Yeah, what I probably didn't, because the gentleman touched upon water coming out of taps, that's a little bit different. We're dealing with closed systems, heating systems, heat pumps, whatever. Um, Water out of taps or showers, whatever, is comes under water hygiene regulations, and um, obviously the issues of Legionella and other bacteria. Um, and water out of taps is drinking water quality essentially. So you can't coat the pipes, you can't do things which people could drink. So yeah, there's two different systems, and today was all about closed systems.
Well, thanks very much, and Nigel, for that amazing talk. And are you okay to do circulate the presentation? Is that all right?
Yeah, what would you like it as? Because I've got it as PowerPoint at the moment.
PowerPoint PDF would be great.
PDF, yeah, I do that.
And we've got the video now. So I'll stop recording.
Okay.